last lesson of the year. 12.3, trigonometric functions of general angles. So, in 12.2, we drew angles in standard position. And now I'm going to show you how to find the trig values of particular angles that actually aren't in triangles. The thing that's kind of important, and I've mentioned this when we were talking about 12.2, is that you can find the trig ratios, the trig functions, the trig values of angles that actually could never fit into a triangle. Okay? And I'm going to show you how to do that first with some simple angles and then generalize from there. Okay? So we have a regular standard plane that we had before. All right? Now, what's different about it is what's written up here. We're gonna come up with theta. Remember, theta always represents an angle. We're gonna let theta be an angle in standard position, and there's gonna be a point on that terminal side. That point we're gonna just generally say is xy. And so in terms of visualizing what that means, we're looking at something like this. Okay, there's some angle theta, right? I have my little curve. I labeled it. I put the arrowhead on it so we get direction from it. You could have highlighted the original side so you can kind of see that angle. All right, and then there's this point, P, that's on the terminal side. That's what all this is saying.
And then you draw like a line down.
Yeah, we're getting there. Okay. Again, we're working in generalities right now. I could have just as easily put a terminal side over here and labeled it XY over here. I could have done it here or here. It doesn't matter. But we might as well start off in the first quadrant where everything's positive, so you can get a sense of what's really going on. And we can find the trig ratios that are associated with theta when I have this point xy on. And it'll work similarly to what we've done before. If I have a point up here, that means I could drop a line directly down here and basically create a right triangle out of this and make this the hypotenuse, right? And so if I did that, it would look like this. So if I drop that down, I know because this point is xy, this length of this particular vertical line is just going to be y. And as you can tell, if I drop it down just right, I create a right triangle. Well, if I know that this height of this triangle is x, what is this length right here? I'm sorry, I said x, I meant y. This height is y. What is this length right here? X. Okay? So that's probably why I said x, because I was thinking about x. So this is what we have right now. Okay? I have a right triangle where one of the legs is x, one of the legs is y. We got to figure out what we're going to call this hypotenuse. And once we have that, we'll be able to find all the trig functions. All right. So what we call that hypotenuse, when we talk about angles in standard positions, we call that hypotenuse R. And the reason that we call it R, like why do we use the letter R ever? Generally speaking in math, where do you see it? What does it represent? Radius. Okay, and we talked about this in 12.2, right? When we're building angles, we're rotating in a circular fashion, whether it's a complete circle, which this obviously is not, or a partial circle. Okay, so that's where the radius comes from, with that sort of center happening right here at the origin. So from this, I could actually write all the trig functions, because as we just discussed, this radius is the hypotenuse. Well, with respect to angle theta, what is x? What side is x? It is the adjacent side. That is correct. And then what is y? the opposite. So I've formed a right triangle there. And so I could write all the different trig functions, right? So what is the sine of theta? Go ahead and write that. Write it down in your notes, what the sine of theta is. Okay. Somebody want to volunteer it? What is it? Alejandro, what do you got? Y over R. How many had that? Okay. So what's the cosine of theta? Just say it. X over R. Tangent of theta. Y over X. Okay. So those are the first three. Any questions about those?
No.
Then if I want the reciprocals, what is the reciprocal of the sine function?
CSC.
Which is the abbreviation for cosecant. Okay, the cosecant of theta is just R over Y. What is the reciprocal of cosine?
Secant.
Secant. So the secant of theta is R over X. And then the cotangent, that's the easy one, is X over Y. Okay? Now, I would say memorize those. Obviously, memorize the first three. However, something that I want you to think about is that the sine function is from this point forward, and especially when you move on from me to go to geometry or pre-calculus, the sine function is always associated with the y. The cosine function is always associated with the x. And the tangent is always associated with the y over the x. These are going to come into play a lot later. Okay? So here it is all typed. Nice and neat, so in case you needed it. So you can always draw this triangle if you can't remember and you can't keep it straight, that the sine goes with y, the cosine goes with x. Okay. The other thing that's important is we're going to do an example here in a minute where we draw a triangle. But the truth is, when you have some of the exercises that you're going to do, you don't ever actually have to draw a triangle if you know the point that lies on the terminal side. Because we can rethink of Pythagorean theorem a little differently for this. Okay. Because if I use Pythagorean theorem for this triangle, what would it look like? Yeah, go ahead. X squared plus y squared equals r. This right here is going to play a big role in what you do today and Monday.
So I don't ever have to draw this graph, right?
You don't. Unless it tells you, unless the problem says, draw it. Sometimes it'll tell you to draw it. But if it just asks you to find the 6 trig functions, for example, of an angle, and you'll see in the next example, I'll show you that, so you'll see how it'll be written. You won't necessarily have to draw it. Now, I am going to draw the first one because I want you to get a good picture of what's going on. But from that point forward, yeah, you don't have to draw anything unless the problem specifically says draw it, okay? And in some cases, to be perfectly honest, you can't draw them sometimes based off the point that they give you, okay? Other questions? That was a good question. All right, so here's a type of example that you're going to have. And this is a good example of just the point you were making. It doesn't ask me to draw anything. It's telling you that there's some terminal side theta in standard position. That point, -3, -4, is the point on the terminal side. Find the exact values. That's important again. It didn't, on your quiz, I had you round everything. You didn't have to find exact values. But for this problem, they want exact values, which typically means leave it as a fraction. Now, I'm going to show you with a picture first. And then I'm going to show you that you could have just as easily done the problem without drawing anything. So, let's see. Now, obviously, what quadrant is -3, -4 in?
Third.
Third, right? You count 1, 2, 3.
And tangents
Okay,
are positive.
so let's think about this. If I'm going to create, in this case, I can create a triangle. Like I said, I'm going to create it. We're looking at something like this, right? So I go left 3, down 4. All right, and so then this gets to the discussion that's being had. We have to know the radius, right? We have to know the hypotenuse. Now, again, you might be thinking to yourself, how do you have a triangle that has a negative side? Well, it's just the direction for standard position. Yes, it is impossible to draw a triangle that has negative length. That's not a thing in real life. But in terms of putting it on the standard position, we can do that because it's signifying a location. Now, this is where I think it's helpful to see. Okay, this is where my point is. And then I can put my R in there. Now, the thing that's interesting about this, and interesting from the, I'm a math teacher perspective, is that this angle here goes beyond 180 degrees. This is the terminal side. But when we look at the triangle, we're only looking at this little angle in here. And I'm going to tell you what this little angle in here is called later in this lesson. But we're talking about finding the trig function values of a angle that's bigger than 180, which therefore can't actually be in a triangle. But this little part can make a triangle. That's your sort of lead. All right, so to the question, the discussion that was taking place over here, is R5 or -5? Well, this is where you go back to your Pythagorean theorem. I'm looking for the hypotenuse, which means I'm taking the square root of this squared plus this squared in order to find the radius. So the radius in this case, which is the hypotenuse, is going to look like that. Square root of 3 squared plus, square root of -3 squared plus -4 squared. Well, so right, when you square both of those, they just turn positive anyways. So the question, is this kind of like a 3, 4, 5 triangle? The answer is yes. A -3, -4, is the radius going to be 5 or -5?
You just plug it into your calculator, it's going to be 5, but it should be -5.
Well, I don't have to plug this in my calculator. This is the square root of a positive number, right? So you can't take a square root and get a negative, right? That can't happen. So my R value, my hypotenuse, does in fact equal 5. So this is, in a way, this is another Pythagorean triple. -3, -4, 5. Obviously, it's related to a 3, 4, 5. It's a very, it's like a
Pythagorean double.
It's like a sister or a brother. I don't know. Anyway, it doesn't matter. So you could use this picture, and we could change this, or if you wanted to, you could write it in as 5 if you wanted to, if you like using the picture. And then you could just find your trig functions, okay? But understand, I could do all of this without drawing anything. I could find R because it's always going to be this number squared plus this number squared, the square root of all of that. Whatever those points are, that R value is always going to be found using Pythagorean theorem. Okay? Now the trick is if you still need to see the opposite side and the adjacent side, then that's going to be helpful for you to come up with the 6 trig functions. If you remember that sine goes with y and cosine goes with x, you don't have to draw anything. And you got to remember tangent is y over x, right? Like I could do all of that just with the numbers, okay? So keep in mind what we've generated here. We have a -3, that's x. We have -4, that's y, and r is 5. That is all you need in order to write the trig functions. Okay? You just got to remember which one goes with which. So let's go through and do it, because it's actually asking us to find the 6 trig functions. So here we go. So the sine of theta, okay, got to have the theta. Sine is y over r. So this becomes negative 4 over 5. The cosine of theta is x over r. Negative 3, again with my 3's, over 5. The tangent of theta, y over x. Negative over a negative.
So
That's a positive. Yes, question?
don't all tangents in the third quadrant have to be positive?
Yes.
Okay.
I mean, those are other observations you can make. Tangent over here will always be positive. It will always be positive over here. It will always be negative over here and negative over here.
And sine.
Okay? So the cosine will be negative over here because cosine is with x. Sine is negative over here because it's with y. So yeah, those are parallels that we're going to be making soon. Okay? And then the other 3 are just flipping them. So if I take the other 3 and flip them, I have cosecant of theta is negative 5/4. The secant of theta is negative 5/3. And the cotangent of theta is 3/4. Okay? So just remember, sine goes with y, cosine goes with x. And unless it tells you to draw something, because it didn't, you don't necessarily have to go through those motions because, again, here's the hypotenuse, here's the opposite, here's the adjacent, and we think of theta as being in there. Okay? But I want us to start transitioning away from opposite, adjacent, hypotenuse and getting closer to the sine is y over r, cosine is x over r, tangent is y over x. We need to get to that place. Okay? Any other questions? So that's the first part of this. The next part is about how we made this little triangle at all. Like this little angle in here was not the angle. In reality, the angle was this. That was the angle, right? Because all angles in standard position start here. So how can I come up with trig functions based on an angle in here? Well, the answer is we have a new term. Original drawing that we were looking at, okay? Let's say this green angle is 225 degrees. I mean, I know that it isn't, but let's just, for argument's sake, say that it's 225 degrees because this line's about halfway in between here, okay? What this means is that the trig functions of 225 and then what's this angle is 45 degrees. Those trig values are all the same except you have to watch out for the signs. Because the trig values for 45 were going to be up here, so everything's positive. So what you just have to know is that, okay, if I'm down here in the third quadrant, then my x and y have to both be negative. And so the trig values for 225 and the trig values for 45, the fractions will be the same. It's the signs you have to watch out for. And that's why reference angles are important. And that's why we can take the trig function, the trig value of a number that absolutely can't fit in a triangle. We can't draw a triangle that has an angle of 225 degrees. That is not possible. The maximum total values of total degrees of a triangle have to be 180. So you can't draw a triangle that has 225. However, we can find the trig functions because of reference angles. Okay, and again, it makes it with the x-axis. Important point to make, and this is consistency. We've talked about this all year. Okay. That new term is called a reference angle. That little angle that we were just looking at in that picture is the reference angle. The reference angle is an acute angle. What does acute mean in terms of geometry?
Small.
Smaller than 90. Okay, between 0 and 90. So you can't ever have a reference angle that's bigger than 90, or equal to 90, actually. Okay, you can't have one smaller than 0 either, meaning you can't have negative angles. So it has to be between 0 and 90. Okay, and that reference angle is formed with the terminal side once we draw it in standard position, and the x-axis, this is really important. A lot of mistakes get made when people try to form an angle with the y-axis. That would be wrong. Just like the example that we just did, that little angle that we were using to come up with our trig functions was the terminal side combined with the x-axis. And here's why the reference angle is important. The trig values of the reference angle will basically be the same as the trig values of the other angle, except you got to watch out for your signs. And I'm going to flash back to that picture here in a second when you get done writing this down to kind of show you what I mean. Here's what I mean. If we look back at if the angle is given to you in degrees, then its reference angle is in degrees. Stay consistent. So yeah, you should know what the next one's going to say. If an angle is given in what? Radians. Then its reference angle will also be in radians. Now, what you will probably do if you're given a situation like this, you'll probably convert it to degrees, work through the problems in degrees, then just you have to remember to convert it back to radians at the end. Okay, since radians, that idea of radians is new to you, I expect you to still work through everything in degrees for now. When you get to pre-calc, you'll eventually get comfortable enough working in radians that you'll do that. But when you're given an angle and you're trying to find the reference angle, if it's in radians, your final answer should also be in radians. Okay, so just be careful with that. We're going to go through two examples. Here's the first one. So this one does say sketch each angle, then find its reference angle. Okay, so we've obviously spent a lot of time over the last couple days drawing angles in standard position. So go ahead and do that. Draw 210 degrees in standard position. Oh, they're over. Here is my perfectly drawn angle that I took from the book. Okay, so hopefully you have something like that. How many have something like that? Very good. Now, the reference angle, so this is angle theta. We just name angles theta. Okay, if you haven't gotten that gist yet, that's the deal. The reference angle is the angle that the terminal side forms with the x-axis. This one right here. Remember, it has to be between 0 and 90. So it can't be this one. So if you're trying to form an angle here, that doesn't work because this angle is obtuse. It is bigger than 90. It's got to be the acute one, which is this one right in here. And the way that we signify that it is the reference angle is we put the theta and we put a little it looks like an accent mark. We call this theta prime. Maybe you use prime in your science classes. Maybe not. If not, it's coming. Okay? Theta prime is the reference angle. And what we have to figure out is, what is the reference angle? And now I'm not going to tell you a formula or something. I want you to think through it. Because, in fact, when you were drawing your angle, you probably already figured out what it needed to be. Because my guess is you started here and you're like, okay, I get to here, and this is 180. How much further do I have to go? So how much further did you have to go?
30.
I had to go 30 degrees more. Well, that 30 degrees more is the reference angle. Okay, so when you express the reference angle, all you do is write theta prime equals 30 degrees, and then we're done.
So do I have to do this, or can I just do
Well, if you notice here, the directions say sketch each angle. So if it asks you to draw it, then you have to draw it. It's like an accent mark. Okay? Now, here's the thing that's important. And here's, again, I talked about it a second ago, and I'm going to talk about it again. Here's what I want you to really understand and why reference angles are important. The trig values of 30 degrees and the trig values of 210 degrees will have the exact same fraction, the exact same value. The difference is Since I'm down here in the third quadrant, the sine, the y is negative, the x is negative, which means the sine for 210 degrees and the sine of 30 degrees will have opposite signs. This one will be positive, this one will be negative. Same for the cosine, since cosine is with x. X is negative here, so that fraction will be the same, except the cosine of 210 will be negative compared to the cosine of 30. The tangents are actually the same, right? That's why reference angles are important, because if I know one trig value for one angle, I can find other ones, right? Now, let's go through on in radians. Okay, negative 5 pi over 4. Now, you could try, if you want, if you are bold, to work through this whole problem in radians. I just don't think you're ready for that. I think the idea of radians is too new. So my first thing before I even do anything with this problem is I got to figure out what that even means, negative 5 pi over 4. So what you might want to do is right away convert it. What do I do to convert that to degrees? What do I do?
180 over 5.
180 over pi. Okay. So then the pi's cancel. Does 4 go into 180?
Yeah.
How many times?
45.
45?
Yeah.
It does. Okay. So now I just have negative 5 times 45,
25.
which is what?
225 degrees.
Negative 225 degrees. So if you go ahead and then sketch your angle using degrees, you'll have an idea where that terminal side ends up. Because where that terminal side ends up is really important. And then you just have to convert everything back to radians. So go ahead and sketch that one out and let's see how you end up. Since it's negative, you have to go clockwise. Don't forget that it's negative. So if you start drawing an angle going counterclockwise, you got the wrong thing. Okay, it's got to go clockwise. All right. So you should have something that looks like this. Okay, when I'm going around clockwise, this gets me to negative 180. Then I got to go a negative how much more? 45. Because this is negative 180. Then I got to go another negative 45 to get me to that negative 225. Well, what's important is the reference angle is not negative 45. Because the reference angle has to be between 0 and 90. Or, in the case of radians, it has to be between 0 and pi over 2. Okay? So this reference angle, all right, there's the reference angle, theta prime, right in there. We're talking about this angle right here. What is theta prime? It's 45 degrees, but that's not good. All right, we gotta convert it to radians. Okay, so not really. We got to put it back into radians. Well, in order to do that, you multiply it by pi over 180. Well, we just talked about how many times 4 went into 180. That was 45. That means 45 goes into 180 4 times. Okay, so my reference angle, theta prime, is actually pi over 4. And just keeping in mind, that the reference angle in radians, this is in radians. I know we talked about acute angles being between 0 and 90. That's what it means to be, that's 0 and 90 in radians, 0 and pi over 2. Okay? So your reference angle needs to be in here, basically between 0 and half pi. This is fourth pi. All right? Notice I highlighted the reference angle in green. So yeah, that's kind of it. So you've got finding trig functions for a point that lies on a terminal side. You got a new way to think about those trig functions using x and y and r. We have reference angles that you'll need to find and draw those angles, and we have some new notation for a reference angle as well. And that's it.